I introduced backreaction research in analog gravity. But today, I introduce mainly analog gravity and also backreaction related and another backreaction in analog gravity. I heard that many people are familiar with analog gravity, so I'll introduce a very basic idea, starting with the thing you are familiar with. So in quantum field theory, in curved spacetime, we have some globally hyperbolic space-time, and this has, of course, pseudo-Riemannian structure. In here, we define some correlation with the time, and this time direction allows us to find the momentum. Using this momentum, we can find some phase space, and also we can find Hamiltonians. With this classical structure, we can quantize this field by assuming three steps. First, we will only consider just a linear free scalar field. We will not treat any complex case because of the time limit, and this is the simplest example. And so there are three steps of canonical quantization in Fock space version. One is first, you complex stuff by the phase space. So phase space is our solution in classical spacetime. And using some Carla manifold, you can redefine vector field as a complex vector field. And also, you can define some complex inner product, but use, for example, Klein-Gordon product. Using this, you can define the norm of the spacetime. I want to emphasize that in this norm, you have this Cauchy surface, which define the vector. So we have some space-like surface. You have some space-like surface, you define the norm, and using this norm, you can decompose the positive and negative norm solutions. This positive and negative norm solution defines also vacuum, but unfortunately, this vacuum structure, so using this positive norm space, we define this positive norm space is the Hilbert space for the solution. And using the basis function of this phase space positive norm space, we can define the annihilation operator. And each complex conjugate is automatically defined by negative norm mode solution, and it can define creation operator. And using this creation and annihilation operator, you can define the vacuum, and also you can have a Fock space representation of the quantum field. But the decomposition of this quantum field is not unique. You can define random choice, any choice of positive and negative norm mode solution. So by choosing different Cauchy surface, for example, you have many different choices. But in Minkowski spacetime, you can always nicely map to using Poincare transformation. You can map one Cauchy surface to the other Cauchy surface, defining positive and negative norm mode. So you can do happily with the field theory without ambiguity. We can define just this family of vacuum is our true vacuum, and we work in only this nicely defined vacuum. But in curved spacetime, you don't have this nice, well-defined vacuum choice, so you have some ambiguity. So there are two different vacuum. For example, if we choose two different decomposition of positive and negative norm mode, you can define. So in here, we have a same solution space, same phase space, but they have a different positive and negative norm mode expansion. Then, of course, basis vector should be different for each positive norm mode, and they define different vacuum annihilation operator and also vacuum. And these different vacuum are related with the Bogoliubov transformation called the Bogoliubov transformation. using this Bogoliubov transformation, you can always change between two different expression of a quantum field in Fock space. Some case only the positive norm mode is still same, so you can define some different bases, but still same positive negative norm mode decomposition. In that case, this beta term is 0, so you can have only positive norm mode to another positive norm mode. But if beta is non-zero, then there are some mode which has a positive norm mode in one solution, but the other decomposition, this is a positive and negative node mixture. So you can think of this as just
what is the reason you have two choices?
There are multiple choices because there is no restriction.
Is it related to actually diffeomorphism or coordinate transformation?
No.
No.
If you find some diffeomorphism or nice coordinate transformation,
If we define the vacuum, we have to define first time-like vector.
yes.
So in that sense, time is a specific in coordinate. So
That's a very important question. In fact, that's what I taught here. We have a nice globally hyperbolic space-time. So we can define time direction first here. But in here, for example, you have I show you this Cauchy hypersurface, but you can choose any space-like surface. So you can choose some little bit angled space-like hypersurface. You can still define the inner product with this another hypersurface, but with this hypersurface, some vectors change the sign. Some functions change the sign. So you cannot sure what is positive, what is negative. But of course, in the Minkowski space-time, this time direction, the Lorentz transformation changes only positive norm mode to positive norm mode and negative norm mode to negative norm mode. So there is no ambiguity. But you can define any random transformation. For example, Lindler coordinate, I'll show later. For the accelerated observer, in that case, you have a killing horizon in that case. So you cannot define with this. I explain a little bit later when I go to that break. Yeah. What I want to emphasize is that there are many choices, and some case, like Minkowski's case, then we have some very nice choice of vacuum. But in general, we don't have this nice vacuum. So there is an ambiguity. One solution is that we give up this box space representation and to the field theory with just local quantities, like only calculating energy momentum tensor, for example. The other choice, what we can do is that define some physical reasoning and find some interpretation of a Fock space. So we want to still keep the particle interpretation.
Question. So I'm a bit confused. So you're saying once you choose the Cauchy surface, that there are two different choices of vacuum, or so I'm confused because for example, if you just fix the Cauchy surface in the normal way, and then let's say we're doing the scalar fluid theory.
Yeah.
Then for scalar fluid theory, we have A and A data, and we cannot use A data as the operator showing the vacuum state, right? Because the commutator, specific sign, commutator of A and A data is one, A data A is not one.
Yeah.
So we do not have that freedom. So my question is, once we specify the Cauchy surface, choose the Cauchy surface, still there are two choices for vacuum. In what sense?
No. So it depends. Maybe I explained wrong. Sorry for confusion. So if we define one Cauchy surface, maybe I go here. I like this figure. So when we define this Cauchy surface, we have two things. One is this commutation relation in quantization, and by developing time direction by just classical equation of motion for the linear theory, we do the time evolution of the field using classical equation of motion. but we keep the quantization in this Cauchy surface by stacking, I say stacking each. So because this has this Cartesian product form, we can stack each step space like hypersurface to make cover full space-time. But we can choose different, I mean, different direction angle, for example, in figure. You can,
It means different coordinate system.
yeah, different coordinate system.
So you're choosing different formation.
Yeah, different coordinate, yes. Then we have different.
Then why there are two choices? You can have infinitely many.
Yeah, infinitely many, of course, infinitely many. This is just what I want to show is that there is a transformation between different choices. So it is just the example theory for a confusion. Yeah. You can choose any arbitrary many. Yes. Yeah, in fact, there are infinitely many choices of vacuum, choices of positive negative norm decomposition. But of course, we are interested in some nice coordinate system or physical meaningful vacuum. I don't want to go detail on every calculation and every mathematical difficulty. What I want to show is that what is the similarity and idea between this quantum field theory and analog gravity system. So first, I show some Ullo effect, because Ullo effect is some constant accelerating observer. His timeline is like this, and this guy have some there is some horizon in between this other part. So there is a horizon for him. Any light coming from left side cannot come to this guy. So this guy is disconnected from, causally disconnected from this other region. But we can also, we can do the also quantum field theory in this observer. We can define full spacetime because Minkowski spacetime is usual spacetime. So we can define just for any space like hypersurface on the full spacetime. Then we can do the field theory with that region. The other choice is that we can, for this observer, if we from this observer's frame, then I show this Lindler diagram for conformal case, what I will say in here. For this observer, every time direction, every right curve goes like this. So this guy cannot see this case here, other H wedges. So one can do the field theory only in this region. Then because this region is totally disconnected to other region, one can do the field theory only in this region one. So what you need is just before, we need a nice Cauchy surface, and then we can do the field theory. So then we can do the field theory. In here, only region one is causally disconnected. One can do the without any other region, one can do the field theory in region one. Or one can do the field theory for the fourth Minkowski spacetime. There are two choices of Cauchy surface. One is this purple line. The other is this blue line. I just read it a little bit down. Just it is just my preference to say relating with the right coordinate. But the important thing is that this region and this region have a different choice of Cauchy hypersurface. It means that they have a different choice of vacuum. If we want to see any particle creation, we need this different choice of Cauchy hypersurface or different choice of vacuum. So different choice of positive and negative norm decomposition. And this comes only from the structure of spacetime, not related with any other their interaction, because we are dealing with just a free field theory. We don't need any other thing. Gravity is nothing special, just the space-time structure, how they curve how they act or how observers move determines they see the particle creation or not.
From the coordinate transformation point of view, and the Minkowski space, actually tensor would be trivially zero, temperature is zero, and the tensor T mu stress tensor T mu is zero, and everything is trivial. And using coordinate transformation, you can get some physical object in the Rindler space. I'm wondering why the triviality behaves non-trivially in a Rindler space. Actually, null tensor transform to actually null tensor.
I'm not sure I understood the question correctly, sorry, but I try to answer. If I answer wrongly, please ask me again. So I think the question is that why just different observers see the different particle content? In fact, there are many interpretations. One is just something like Birel and Davis. It is that because observer is accelerating, one can define this observer as some simple detector, right, called Hollow-Day detector. In that case, the acceleration of the observer gives energy to the particle detector, and it creates a summer wave. That is one interpretation. This is more common and useful. For example, using this, just what you need is observer's acceleration. So one can define some rotating observer, I'll explain later, or some randomly moving observer. If they accelerate, they can see some particle creation.
So particle would be acceleration, external acceleration.
Yes.
There is one question is relevant to the purpose of this question. Is the particle creation, so when you introduce the whole transformation.
Yes.
So and also two objects. One object is finely costing, the second object is accelerating, and through the whole transformation you could make some particle creation.
So this is the second reason I wanna say, because this first is nice, but it is not related to the Bogoliubov transformation directly. The other is so in this Bogoliubov transformation approach, one needs some horizon. But as I told you, if there is some random movement, the horizon is not well defined because in this Rindler coordinate, one is accelerating constant acceleration. It has horizon behind it, 1/a. But so in this case, horizon has a very important role. In this case, one can think, so we have this full space-time
For static object.
for static observer. So we have a field theory for just flat space-time. The other is that we have also field theory, but with only half of it. We have only half of the Cauchy surface. It means that we trace out this part. So tracing out this part makes some summer excitation. That is another interpretation.
Who accelerates the region of I? So I think that you consider two observers. One observer is a static observer, flaming out space time, and the other observer is accelerated observer. The viewpoint of accelerating observer, only the region I is available. In that, the space time is Rindler observer in the space time and particle creation.
Maybe I need to also explain this more. Because that's a good point of view. Because when we say just observer, we usually say local particle detector. But when we use this Bogoliubov transformation view of quantum field theory, we usually say more about global structure. So there are just two vacuum for. Of course, we can say it is also observer because we need a full spatial slice as a hypersurface. So we need some initial condition. Not just we are measuring here. We assume that we know full initial condition. That's the difference. So I say set of observer may be more good explanation. Every observer has the same stationary. These guys can say it is vacuum. The other observers, set of observers all accelerating to the right, then they can say also something. In this case, so these other accelerating observers, so these other accelerating observers, they can say also we are true vacuum, but in here that's where we need some physical reasoning for vacuum. Their vacuum are mathematically equivalent, so one cannot say it is a true vacuum or this is true vacuum. But our physical sense says that stationary observer is more reasonable, right? So we believe this stationary guy is or some inertial frame. I say inertial frame. Inertial frame in Minkowski is more reasonable. So we assume this is vacuum, and then we say this guy is the particle creation. If we believe this guy, and I think this guy is vacuum, is true vacuum, then if we do the Bogoliub transformation, this guy will see particle creation also. Thank you for the question.
If accelerating observer emits a photon to the negative x direction,
Yes.
that photon will go to the region 3.
Yes.
What means? Still, the accelerating observer lose any information.
So what we wanna know is that from our initial Cauchy surface, so initial data of the field is distribution. Can we know at some time our field distribution?
Actually, there are no net flux.
Yeah, it's not for
Yeah.
just time direction. Actually.
No net flux. Actually, there's no loss of information.
Yeah. So this is infinite. So this is a conformal diagram. So it needs infinite time to go other direction. Yeah, and I say what we are more interested in is just there is also going right to this direction. But what we want to know is that only this region, our whole space-time is in this case, this region only. So we don't care about outgoing that case.
This question is, I think, how about the influx from section 1 and section 3, then maybe information would be lost. My answer is, I think, actually some equilibrium, no net flux.
Yes, there is a little bit tricky because it is also related with this black hole. So yeah, I cannot answer clearly for this question. Sorry, but yeah, yeah, there should be no net flux, but because this is just this is a different case because this is just vacuum to vacuum transformation. But question was, can we send the right to the left side? Of course, we can send the right to the left side.
It doesn't take infinite time. Or the
Sorry.
through
That's my fault. This doesn't need infinite time. So we can send it because this Bogoliub transformation is just the transformation between state and state. But if we have some sending right to the left, there's nothing break.
Then the space-time would be non-static, actually, if we emit some photon. Non-static. This is the static story. Static geometry.
Yeah. Yes, you're right. Yes. Okay. No, but it's okay because okay. In real Minkowski real time, it is okay. It has finite time. And this linear time, I think it will take a minute time because it is other edge. I think that gives the solution why they have a different. So the field theory or in this region are consistent only in this linear coordinate region.
Your title of talk is Backreaction. So I think
Yeah,
Backreaction causes non-static drama.
Yeah. That's true. Yeah, that's a difficult thing. Yeah. Okay, I go next. Famous this black hole. I think most of you are more familiar with this black hole. So using gravitational collapse, because of gravitational collapse, the light comes and it sometimes go out. So light go to the black hole. If it is just out of before horizon front, it will go out. But if not, it will captured. This is a conformal diagram. So as this proper colored part is inside the star is collapse and the event horizon forms here. But this is a little bit complicated to say something, so I changed it. Very simple case. It is called the radial spacetime. So you have just null light shell comes into one region. So there is some spherical shell of light comes to one point. Because they will shrink and shrink, at some point it will make horizon. So this is the simplest case of finding Hawking radiation. Because the Hawking radiation, it was shown that Hawking radiation do not depend much on the details of collapse. How it collapses, it is not matter. So they will give similar result. In this radial spacetime, one can find it easily. If outside of this cone, four horizon forms. Inside, it is just a Minkowski, and it is combined with the Shubarovsky spacetime. And we can do similar thing. I showed two. One is some traditional way of defining Cauchy surface. I just want to say there are two different Cauchy surfaces. One is ingoing waves. The other is that outgoing wave, which is what we want, and the other is horizon. Of course, horizon has many problems, and one needs to solve this horizon problem by going backward in time and things to solve this. But that's not what I want to talk today. I want to talk is just you can choose different Cauchy alpha surface to find the particle creation. And in this case, we have only this outgoing region. Volume transformation to here to this outgoing region to find the particle creation. And what Ulu find was that it is very similar to just Hopsky spacetime. If we cut here and cut here, it will look. Sorry. If we cut here, it looks very similar to this. So this is our Ulu spacetime, but I cut, which looks like black hole without any horizon and singularity. So, but Ulu's point of view is that because what we are interested in is only outgoing wave, then if we use the Lindler coordinate, so if the horizon is the same, so if we put the observer at the near the horizon, accelerating with the surface gravity, we will have the same particle creation by Hall transformation. And this more nice thing is that this can be used also for eternal black hole, not just collapsing black hole. And so using this, this is start of analog gravity. So the idea is that until now, what we know is that only global structure of space-time determines particle creation, black hole Hawking radiation, and every vacuum choice. These are all determined by just choice of space-time. If we can find some effective space-time, which have a similar structure of real Lorentz geometry, we may find some quantum field theory Hawking radiation or cosmological particle collision or things in other system. Why this is nice? Because we cannot make black hole, we cannot make universe, we cannot expand it, we cannot do any experiment for this nice, very beautiful particle collisions. But using this other system, if we can define this space-time, we may do some experiments. So his first idea was that using the water, I explain more formula later, but so he says some fishes swimming in the stream of water. If these fishes are just talking with each other by sound wave, they cannot see any other, they just talk with sound wave. Instead of light, their communication is sound. So instead of light cone, they use sound as their knowledge relation. And this is each light cone. This is some horizon if there is some water flow. Because this flow is so fast, so sound cannot even go upward. Then it is like a null ray cannot go upward outside of this region. So we can say this may be black hole. And yeah, one of a system I explained a little bit later. So you can define really this system have this type of Hello diagram. Then how we can make this space-time? It is just simply linearizing the fluid dynamics equation. This is most classic and basic approach. So we have two equations for the fluid. It is not just fluid, we need barotropic, inviscid, and rotational fluid. In that case, we have two equations. One is continuity equation, of course. The other is this Euler equation. And by linearizing each one, we can have first order equations. Using this first order equation, if we reformulate it, continuity equation becomes something like just Klein-Gordon equation.
What is phi?
Phi. Sorry. Phi is velocity field, so linear. So continuity equation is density, time derivative of density is number of density times velocity, and this h is enthalpy, and phi is a velocity field which defines velocity by just derivative. And this first, just phi one is linearization of velocity field.
What is the meaning of Euler equation?
This is some simplified version of Bernoulli equation because it has irrotational and inviscid and barotropic. These conditions make it more simpler version. So we can have this nice form of equation if we define metric like this. In 3+1 dimensional case, and it is a similar form, but this vector changes by dimension also.
So phi one is fluctuation,
Yes.
and phi enters into the metric because there is V.
Yes.
Background is the geometry, and fluctuation is living from fluctuation around that background.
Yes.
So, what do you mean by barotropic assumption? What do you mean by that?
Barotropic means that this pressure is governed by only density, only function of density. It is barotropic. And yeah, this needed for this simple equation. And this is just a finite Weierstrass form of the metric. So because the left function is just simply c square minus v square, you can easily find the horizon. Because the sign changes just when c square minus v square exceeds v exceeds c or v is less than c. So it is consistent with our intuitive view of the fluid.
that is very similar to the real hydrodynamic equation.
Yes.
In order to avoid shock formation, we usually transform the original Euler equation into the hyperbolic. So that the equation involving the metric is like that. That means whole system is transformed into hyperbolic conservative form. So that is very we are actually that is the equation we are solving.
That's very
So, but we haven't considered.
Yeah, that's very nice information I need to know. Thank you for telling me. And
metric form, there is some still there is some component of zero I or I zero component. Is there any momentum transform?
I don't think that is a real.
Yeah.
It just
How can
yeah.
you take?
Actually, if we transform the original equation into the conservative form, in every place there should be boosted terms, just like that. C square minus B square.
I mean, in GAD, there is zero I or I. The V7 or
Oh, including continuity equation, the Euler equation actually has 3 dimensions. So 4, there are 4. So that's just the I mean this is 4 by 4.
Yeah, this is 4 by 4. But I mean that the component of the zero I or I zero part. Right? Yeah.
this one.
Yes.
Yeah, this is just the VXY. So
Yes.
this is a little bit bored. Maybe I the better right here. Directly. So Vx, Vy, Vz, for example, is minus Vx minus Vy minus Vz. And this is a 3 by 3 matrix.
Yeah.
Yeah. There is a other thing about division, more on degree of freedom. In usual metric, we have a 10 degree of freedom, but unfortunately, here we have only density and velocity. So we have a less degree of freedom we can use. So there are some restricted systems we can make. One nice thing is that fortunately black hole and many interesting space-time we can make. The other is that in here, I assume that very simple fluid, MBC the barotropic and things, but I'll explain. We don't use just fluid, we use every other system. In fact, any Lagrangian, if you linearize and if you do the linearized theory, you can always make equation of motion in this form. But only difference is that in that case, you don't have this simple Lorentzian metric. You have some different space-time called the Finsler or some other. So metric has many components in that case. But anyway, we can always define this simplified form of equation. Yeah. So then what we have done. So this is simple figure. So instead of astrophysical black hole, we make some horizon, usually using sound wave. And we try to find some Hawking radiation in the lab. And there are, in 2008, using optical fiber, they use optical soliton as a black hole model. Using this, they find some Hawking radiation. And the other is that this is very interesting because this is just using water wave. Because the linear theory does not depend, because linear theory, time evolution is the same with the classical theory. We can just define some mode decomposition and we can find the particle creation in the also classical fluid. So they find this one, but people are a little bit suspect because it is quantum effect why you find only classical. And this has some problem because it has a not nice dispersion relation. Recently, these two are using Bose-Einstein condensate. Bose-Einstein Schutterite condensate has a very nice description because it is well described with the fluid analogy. And also the other is that the dispersion relation is near zero. So in the infrared limit, it becomes really just the usual light cone. One can map directly to the near gravity Klein-Gordon equation. So these are all experimentally observed. So our goal was a long time goal was this thing. So people do many different things, but this Hawking radiation is the main thing we want to find. And I just emphasize with the Backreaction. Also, there are many other things: radius, dynamic Casimir effect, causality, post vacuum decay, and record instability, Kogenmar mode. These are all done, or people are doing some, not many, mainly Hawking radiation. And there are also many different systems because we can use just fluid, just normal fluid, and Bose-Einstein condensate. Nowadays, people are interested in polariton for the right matter combination, and some dielectric media, optical fiber, some solid state. It is not that much, but also there are some people doing superconducting circuit. And using trapped ion, one can expand this trapped ion to make an expanding universe. And also doing some Casimir vacuum, or some people do, I heard some guy using real astronomical fluid flow. They also do analog gravity in this real astronomical. This is very weird for me, but I'm not sure what he's doing. He just find some magnetic flow or something and do the linearization and do some. It was a very ambitious story. I just heard from some guy. So it is very interesting.
Maybe I'm mistaken. So the supersonic flow is essential in this story one.
Supersonic flow. Supersonic flow is important because supersonic region is where inside the horizon.
Space time.
Yeah.
So supersonic motion is.
Yeah.
Then I'm not sure, but except for the Bose-Einstein condensation, if you imagine the flow of usual fluid, then there should be some shock.
You mean shock wave in Riemann? Right? Yeah. So also that's also a good point. So there are many people doing other systems. Unfortunately not me, but one of my former colleagues, is doing this Riemann wave. And because in here, because I want to say just simple case, I don't say anything about what is this sound wave, sound velocity, and what is this C and density means. One thing is that we need the density in front of this. So if density becomes abruptly change, it means that, and also to define sound wave, one needs some approximation to make that there is not many oscillation in the background. One of the problems is as a Riemann wave, it propagates, it will become more and more, it has some shock. I think you mean this one, right?
Actually, in hydrodynamics, we know the reject solution.
Yeah.
So
Yeah, there are shock wave. So then can we interpret this also as a dislinkage? And pick one, some people do about it, and their solution is that then we can say something about negative singularity using this shock. That's what I heard about this shock wave.
And if you think about the shock, the V square is the overall G square. G square means that something sound velocity, and the signal will be changed in GAB.
if you think that is the geometric, then that might be problematic. But in the sense of solving equation,
Yes.
we don't
So-
encounter any issue.
I mean, when people have a shower, and
Um,
people with the C if the system velocity of sound wave, yeah, free scale, yeah, free scale is over the system. And the signal flow will change. Then,
Yeah, but
then the interpretation goes up. When you equal the sound.
I don't see,
So,
don't worry. If I understand
discuss
correctly,
later.
just by simply make a transformation with Bruce, you cannot make Minkowski transform into that GA.
yes.
So you're solving hydrodynamics in Minkowski spectra and even GR, general relative case, we have pools and formally. So
Yes.
comparing with that, I'm not sure whether I should agree that is cheap or.
If I understand correctly, one can solve a fluid dynamics equation fully correctly, right? And
Yeah.
then why
So-
we do it? So this is
In general,
Yeah.
the shark developed 5 states solution. So usually, in general, there are actually three states and 2 waves, rarefaction and. So, well, if you imagine some limited situation, just like producing only the this kind of discontinuous, well, then we may find some additional features, but in general, the hydrodynamics develops rarefaction wave and continuity waves and there are 3 constant states.
But also to have that effect, you need the nonlinear effect, right?
Nonlinear by which sense?
Their
Euler equation itself is
interaction.
nonlinear equation, so it should
So
develop.
this is linearized theory, so it does not capture that effect. So I
Linearized sequence is
in here, yeah, we linearize the theory because it is only a story
So
about
there's no
the
sharp.
yeah. If we do only this no sharp, if you wanna sharp, you need a high order.
Yeah, initially we can make a discontinuity, then that will maintain the shape.
Yes.
So it's not realistic to me.
Bose-Einstein condensation.
Yeah, so I made the exception for that.
So I not say every that's why I say every fluid don't have this nice view, but one is that linearization gives this form of equation. First thing I want to say is this one, and second is that in reality, then what we can do really? I think that's also a good question. I have to find some solution. Of course, we cannot do any fluid, but if this is linearized theory, so we have a limited description in some short time. If we want to say some real fluid, and if we find some nice interpretation on it, why not we do it? We can do the same story in the short time. Then what is this other way? Then that is today's topic. Backreaction can enter. So how can we say more about this using this linearized story? How much we can say this nonlinear story? That is, I think, the next step of this analog gravity.
Where you get this formula for P1, the fluctuation of pressure. P1 on top line, the P1.
P is defined from enthalpy. So in enthalpy, it's this form. When you linearize, it becomes this.
Why P1 has this time derivative of phi1?
So this is Euler's equation.
That has only one time derivative. I wonder why your final result has 2 time derivatives. Where does it come from?
So this one, P1, we can write rho one using P1.
So there is a
one
time derivative y on the
one time derivative. And then what we do is that we use only Euler equation. What we do is that put this in a continuity equation, linearized version, because linearized continuity equation is the time derivative of rho one. You have a time derivative, this one. So they have a second order derivative. This is how you get second order derivative from this equation. This answer.
You use the powerful number state.
Yes. No, it is just, yeah, P when defining P1, yes. Okay, then I keep going. So, yeah. So we already found many Hawking radiation very recently, in fact, just several years ago. So what we are trying to do is that, what is our next step? So we find our main goal was Hawking radiation. So almost every people were doing Hawking radiation. So now what we can do more? So nowadays many people are doing normal mode because now astronomically people are interested in. So we are trying to find the quasi-normal mode using some analog system. The other is that super radius. Super radius is just if you send some particle into the rotating black hole. In some case, this wave amplifies more because negative same region, negative norm mode appears inside the algorithm. So you can have some amplified reflection. The other is that force vacuum decay. This is a recently started topic. People are very interested. Some people in Nottingham doing that. What they are trying to find is that because what we are doing mostly was just simulating the existing theory. So we do numerical calculation or theoretical calculation separately, and we expect this to be happen. This must be happen, and experimentally we find it. This is very interesting idea because it is opposite way. Because this force vacuum decay is not easily calculated with numerically or analytically, but people are trying to make an analog system for this force vacuum decay, to making some vacuum collision using analog system. They are trying to find the solutions using this real lab experiment. So this is some new way starting. And the other thing is just in entanglement harvesting. There are some people because if we have two different detectors, they have their own spacetime. So their vacuum may be entangled. So using these two different detectors, people might think that we might find some entanglement of vacuum. So some people are doing this. So recently proposed the experiment is that just we can define some rotating laser in the BC. So because the laser is 1 point, it can be, if each interaction can be interpreted as a local interaction with the space-time. So using this as a detector, if they move two different laser, it means that two different accelerating observers, one can say, then they can find some entanglement harvesting. The other is backreaction. So I explain more about this backreaction. Very simply first. There are usually, I didn't find many about this classification, but I find only one paper saying this classification. So there are three different categories of backreaction. One is, so just the classical backreaction is that when some people do cosmology, they assume that space-time is fully flat, isotropic, and homogeneous FRW. But in real universe, there are some errors. By looking at the stars and things, we can find there are in fact matters. So classical backreaction is just what we know. This is just classical energy momentum tensor. There are some other cases. This is called semi-classical backreaction. Usually, so simply we can use just classical equation of motion for Einstein equation, but with the quantum method. So using effective action technique, we can say find some semi-classical Einstein equation. And what I can find in most of the paper is just semi-classical backreaction usually. We have some nice classical Einstein equation. So we know the source of the equation of motion should be vacuum expectation value of the energy momentum tensor. So we want to find it. Third is that quantum backreaction. This is more talked about in the analog gravity because quantum gravity, we don't know much. Maybe there is, but I didn't find it yet, unfortunately. So there are some story. We don't know if we know real quantum gravity or if we know full evolution of full action of space-time, including gravity and matter field. We can find the discrepancy between this linearized theory and this quantum theory. We can find this difference and we can tell this is backreaction. Because we already know semi-classical backreaction, if there's some difference even between that, it can be called quantum backreaction. So this is just a normal way. What I see usually when I search some backreaction in usual cosmology or things that I'm not good at searching, but what I always meet is finding this effective action approach to define this energy momentum tensor, and just energy momentum tensor is a vacuum expectation value of this energy momentum tensor can be defined using effective action. This is of course a very difficult topic because we need to normalize this energy momentum tensor. It is not easy. So I can do it. What I do is that backreaction in analog gravity. Yeah. One nice thing of this is that of course, we can define energy momentum tensor with the same technique. There are some research doing this same effective action technique. So using some acoustic record, one defines some 1D fluid flow using called the Dirac nozzle. So it is that some black hole white hole configuration. And one can find some action because when you go back, this is just the matter actions effective action, matter part of effective action. If we know matter Lagrangian, we can calculate just the same technique. So this is all doing but by that technique. But in this paper, 2005 paper, they do this effective action approach to using different representation. So in Bose-Einstein condensate, one can describe the field with the density and phase. The other is that just the field operator phi psi, if we could. These two different representations give two different effective action. If we do the effective action with the fluid representation, unfortunately, there is some divergence occurs, and there are some terms which we cannot find in the field operator representation. So also, fortunately, in Bose-Einstein condensate, we know that field operator description is more well behaving because it is just many-body quantum mechanics. We know full story, so we know we have to choose. In that case, we have to choose this field operator representation. But so from this point, we are thinking about, so then we cannot use just a simple effective action approach. What we can do, we have to do is find the meaning of backreaction and making model, how to describe it, and then making some solutions. So all of this, so this is just a simple, this is a simple Bose-Einstein condensate expression of backreaction. This one is just using fluid dynamics equation, and they define their own backreaction. And these two, in here they also define some backreaction using also finding the difference between quantum many-body evolution using beyond linear approximation and just effective action approaches difference. This is a very recent paper, and this is one interesting reason because in the beginning, I told that there are not many papers about the dynamics of gravity. They usually give up or they are not interested in dynamics of the space-time. These guys try to make using backreaction. Is the original meaning of backreaction is that the matter field acts as some dynamical source of the equation of motion for the background space-time. They find some relation between scalar tensor theory of gravity with this backreaction. So,
Sorry, I lost you a bit earlier. What do you mean by what do you mean by that the matter field doesn't affect the equations of motion in classical chart? Like 1 page before, in the first, just before that.
sorry, maybe I tell wrong. So, sorry, maybe I tell something wrong. So, in here, what they all do is that just to use your approach using effective action technique. So, when you derive this whole story was about linearized field theory. So, in linearized field theory, we don't assume this matter field affect the space-time. So space-time is static. They are given already. So using this given space-time, we do the field evolution of the matter field. So in that sense, gravitational field is not affected by the matter field, but this back reaction is the linearized. Then we can do this effective action or something to find how this in reality they should be changed. So we are trying to find how they change.
How to define vacuums?
Where?
Vacuum expectation value stress tensor.
In here.
Yeah, vacuum.
That's very good question.
Yeah, if I know correctly, usually people do some find the Gaussian state. To define this, maybe vacuum is not good expression, maybe some Gaussian. Yeah, I heard some people use this Gaussian state, which has
Picture?
No, I mean that's the Gaussian state, which has the same behavior with the classical management intensity. Yeah, or yeah, some case they define some physically reasonable vacuum. Just for example, if you have some expanding universe, you can define Minkowski vacuum in the outgoing region. So there are some choices, but I'm not much familiar with this stuff. Some people are doing this, I just correct.
Your gravitational action is Einstein-Hilbert, or can it be more general?
Usually, this is not my opinion. This is what people usually do. Usually, it is Einstein-Hilbert action, but recently I see some people doing some modified gravity to define this action. So because
You have only metric.
Yes.
But in your previous example, metric was built out of one scalar, phi. Yeah, phi determined all rho and v.
Yeah.
Yeah, right?
Yeah.
The phi satisfy its own equation of continuity and one equation of motion.
Yes.
Do they compatible with the vacuum Einstein equation?
That's very okay. Good to know. Yeah, that was one of the most critics analog gravity people get. But this is not gravity. They don't follow any dynamics of Einstein equation. So that's why I tell it is not related with the dynamics. So we assume Einstein equation is given. And yeah. So
You have to relate the geometry GE.
yeah, so
Yeah.
we are doing curved space-time, but we don't know the dynamics because dynamics is so we have this method Lagrangian.
And how to get the back-reacted metric?
Yeah, if the background doesn't satisfy any
Yeah, so in
gravitational
other words,
equation.
how does space react to matter if you do not have Einstein's equation?
It doesn't matter. I say it doesn't matter. It doesn't matter is maybe not good answer. Because what we can find is that because this is some action for the method. So we can still write this. This is just the fluid equation. But this density and phase can be written as a gravity metric. So we want to find some relation between metric because energy momentum. It is not.
In equation one.
Yeah.
Actually, capital GAB in equation one.
Yeah.
Capital GAB should be related to your wave equation.
It is not that simple so this is for not analog gravity. It is just usual.
And how to relate the small GAB?
So
Capital GAB should be related to
Yeah,
small
exactly.
GAB.
So
is the
capital
capital G
GAB
and small g.
is not the form of Einstein equation.
It'd be something else.
Yeah, it will be something else. We don't know.
Point is
Then
that you
how-
don't care.
Yeah, how to get the Back-Next metric? Actually, we have to solve the equation one by evaluating stress tensor.
But
What we
G
have
is a fixed function, right?
yes,
G is fixed, whatever it is.
yes.
It's not something, not
So-
Einstein gravity, it's something else.
It is just different.
It's a back reaction which is different from gravity,
Yeah.
but it's a back reaction.
Then, you mean there's no Back-Next metric?
You know?
Metric should be Back-Next.
Yes.
Then capital GAB should be known. Explicitly specified. By solving differential equation or equation one, we have to get the Back-Next metric. After calculation of stress tensor, Back-Next the value of stress tensor and put there and solve the total equation motion. Then we can we can get the Back-Next metric. So in this sense, we have to know capital GAB.
And solve it.
Yeah.
Solve it for G,
GAB
for small g.
is the
Actually,
full
TAB
Einstein tensor or just the top of one?
So this is just Einstein equation. So it is just
So
Einstein
the
equation.
system is
So So because what confusing is that there is a real gravity backreactions, there is analog gravity backreaction. I didn't explain analog gravity one yet. So this is the real gravity backreaction equation. The question was can I just spell it? Is it GABUS? Do we know their form or? We know the form of course because this should be just the fluid dynamics.
Yeah.
So yes.
Yeah. So are you using Einstein tensor?
No. This is just not. This
Then
is
what
not.
is capital G?
What is capital G? I don't write it, and we don't write it because what we are interested is just relating, and the other is that because it is easier to just it is later maybe. I'll explain a little bit later about this motion because I explain a little bit later. So about sorry. Yeah. When I go a little bit more, I'll explain later. So yeah, I lost what I was doing. So okay, I go quickly. Yeah. So they find the backreaction has some problem in effective action approach. So they wanna find some nice model describing this backreaction in different analogs. And also, yeah, this is recently what I'm most interested in and people are doing is that so we can find this backreaction. If we can find, we can calculate and we may find some measurable effect from it. That is what we are interested. So this is just electric field. If we have just quantized the electric field, nonlinear electric field, we can use this equation of motion. This is classical equation of motion. This is so this is Gauss-Odor. This is linearized, and this optical nonlinear equation in optical fiber has the same form with the Bose-Einstein condensate. In Bose-Einstein condensate, they also describe this classical equation of motion or gross fit axis. And this linearized quantum fluctuation of this equation. And what we want to find is just the evolution of this density and classical density and phase. Unfortunately, so I say this is background, this is quantum field, but as you pointed out, there is no relation. This dynamics of this is not affected by this one. Then how we can define backreaction with this description? We needed to find another background which contains backreaction effect. So what you need to do is more high order expansion and find the linear term and nonlinear term. Zero solution. So I go a little bit quickly. So what we want to do is that, so using this, so what we can do is that is beyond the nonlinear expansion and define another background space type, define another metric, and find each effect. So what we do is that this is number conserving expansion. So in Bose-Einstein condensate or many-body quantum mechanics, we have a nice expression called the number conserving expansion because original Gross-Pitarski equation or the linear Schrödinger equation, they have U1 symmetry, so they have their total number of particles should be conserved. So there is expansion called the number conserving expansion. It is just keeping total particle number. And this is there are some other approaches. What I prefer is this just using second order. One can do only second order, but just the classical field. So then we have now two classical fields. One is this one, the other is this one, and just a linearized field. And what we find is that there is another equation. So still, this is equation of motion for the classical field, but including quantum source. So classical field dynamics is affected by the quantum field. And so what we do is that some simple system making some finite homogeneous Bose-Katz. And then this classical force, what we write is just when you get normal effective action approach, then you will get this equation of motion. But if you really do the quantum evolution of the full Bose-Einstein Bose-Katz, then you have some different evolution of the current. This is the difference is called written in FQ. This is what we define quantum backreaction force. So this is the one result. What I wanna show is that in here, in the former another paper, they also find some preheating. Sorry, I go backward a little bit. I forgot to try this one. So in this paper, they do this preheating simulation using also Bose-Einstein condensate. What they do is that they find is that backreaction reduces the preheating. So if you include the backreaction, the simulation of preheating is reduced. They use some other method, not number conserving expansion. It is called the truncated Wigner expansion, but it has some defects. So I prefer this number conserving expansion. And using this, we can fully solve analytically the solution. And we could find also there is so if you see the edge of the condensate, because of it, there is some sharp peak of classical force. So it has a very strong suppress on the fluid. But if you include the quantum effect, so this is also backreaction effect. This is just when you consider normal classical fluid description, the effective action approach with the fluid description, you have this dotted line. So you have a very almost looks like divergent. It is not divergent, finite, but very big force because it is potential force pushing to the center of the condensate. But if we consider also quantum effect, this quantum effect, which is not included in the semi-classical effect. It reduces for the first, and if you calculate for the full force, it is almost normalized. And the other is that then what you can measure. So what we are interested in is that how we can measure some backreaction effect. The other is that just sending solitone, because one of the most classic experiment of finding black hole was sending solitone and make some propagating wave inside it and find some horizon. And if you send the solitone using just inverse scattering method and quantizing similar way, but only difference is that now we need to define some spinner to describe this field, but we can still find a nice expansion of the space-time, and we can do the field theory. And one can find some specific shape of the photon number density distribution. So this is also what we hope. It is very hard because it is very small numbers, so it is not easy, but we hope in future we can find some effect of this one. And okay, before going to summary, maybe I have to answer the question of how. So we don't know the GA before. We are not interested in GA before, but metric can be written new metric because now we want to describe the metric.
The Backreaction, we are talking about is actually modifying the potential in the sound wave equation, right?
Yes. Yes. So because it is same, right? Because you can say Einstein equation also modifying the. Yeah, you already find the answer. So just this is all of my talk. So what I want to emphasize first is that I want to advertise analog gravity. Incorrect. So analog gravity is nice quantum simulator, and you can find the various space-time. If you are interested in kinematics of quantum field theory, you can find a lot of interesting story. So analog gravity is a nice quantum simulator, and also because I'm doing mainly backreaction, because I want to say what is backreaction. Backreaction is just the effect of time. So how dynamics of the classical field or background changed by the matter field, and because it contains nonlinear effect. If we want to say some dynamic revolution of the space-time, we need to find this backreaction effect, of course. And yeah, analog gravity. Because of time, I didn't explain much about this one. But one nice thing of analog gravity is that one of the most hardest part of field theory is renormalization. But we have already started away because we know many about quantum mechanics. We can use always this solution. We know already full solution, even though it is very hard to calculate. One can find a submatch to this to find more easily. And also, if you are interested in non-Lorentzian geometry, analog gravity is also good candidate, because if you give less restriction on the condition for the space-time, you can get different metric easily, and you can see some quantum field theory effect easily.